Okay, so maybe for this lesson, as always, pencil, calculator, things like that, highlighter if that's for you. But also, I think for this lesson, I want you to pull out your phone. Don't go on Snapchat, but I want you to go on, you might already have this app if you had myself or Mr. Todd. It's called Desmos. You ever heard of Desmos? It's an app on a phone. This is probably the best free graphing app that you can possibly get. And like, it's good and it's free. So we do like that. And to be honest, I think downloading it right now in the school Wi-Fi, it won't take too long. It's a very small. I shouldn't make any promises actually about that. I have no idea what the school Wi-Fi is like. But this is essentially what it looks like. Desmos. This is our Cartesian plane. It's great. We love it. Take a minute maybe. Play around. You could type in lines, y equals 3x plus 1, and there it is, right? And the beauty thing about Desmos is that it kind of knows what you're looking for. I mean, math people got together and created this thing, so they kind of know what math people are looking for. So like they had the x-intercept already ready for you. They have it right there. It's already lit up. And same with the y-intercept. They're like, yeah, we got it for you. There's some other cool stuff you can do. I'm pretty sure if you wanted a table of values, it'll also provide you with that, which is really cool. So if you're looking for specific coordinates, like it does a lot of good stuff. And for us in grade 10, who are already professionals working with lines, this is going to become super handy for questions like number 9 in the homework from the other day. Like, what does this look like? You can plot those two coordinates and kind of see it. You can see it happen. If you need a hand working with Desmos on your phone, please let me know, because I know using a computer is probably a little bit better. When it comes to doing exponents, it could be a little bit tricky, but it very much works like a calculator. So it'll become super great. Okay, folks, so far, up until now, we've been working with quadratic relations in, where are we? What's going on? Please. We were working with quadratics in this form here. Remember the ax squared plus bx plus c? We've been always working with that. And does anyone remember what we call that? It might be a little bit of a stretch, but yeah. Yeah, we call that standard form. So we can write that right here, standard form. Now, standard form has actually got some benefits. And I think at some point, whether it's on a quiz or a test, I'll ask you what these benefits of standard form are. Because there's 3 forms in total we're going to look at in terms of quadratics. It's kind of like, okay, have you ever seen Spider-Man before? The new Spider-Man actually just came out, right? And how many Spider-Men, oh, I don't want to ruin anything. There were, okay, maybe I should change this analogy so I don't ruin anything if you're planning to watch. Oh, we have a visitor. Wonder if they've watched Spider-Man.
That Toy Story. I've been chosen. Okay.
So back to Spider-Man. Spider-Man, does anyone know his name? Right. And Peter Parker and Spider-Man are the same thing, but just in a different form. Very much like the forms of quadratics. It's going to be standard form. Today we're learning something brand new called factored form. But they truly mean the same thing. They're talking about the same function. It's just in a different form. And each form has pros and it also has cons based on what you're looking at. So standard form. We love standard form because that c value there, that ax squared plus bx plus c, that c value is always the y-intercept. It always is. It's great. If you're ever looking, hey, what's the y-intercept? Boom, there it is in standard form. What we also like about it is that a value. That a value tells us whether the parabola is opening upward, like it's smiling, right? It's positive when it opens upward. Really happy about that. Woohoo, right? Now, sometimes the A value might be negative, in which case the parabola opens down. And we know that because the parabola kind of looks sad when it's negative. Yeah, I know, that could be a little, I get it. Okay. So that, up until now, that should be kind of familiar, or at least they're like, oh yeah, I remember that, C value, y-intercept, A value, opening up or down, great. Now we have this new and improved form. It says a quadratic relation could also be expressed in the form y equals, there you go, y equals A bracket, x minus s, close bracket, open a new one, x minus r, which is very, very weird. It looks nothing like standard form. There's not even a squared in there, right? But there are two x's. So such that r and s are integers. So r and s can't be like 2.5 and negative 4.8. They have to be integers. Integers are basically all of the whole numbers, 0 to positive infinity, and then 0 to negative infinity, but not the numbers between the whole numbers. Those would be rational numbers. Okay? Remember that conversation with Mr. Todd or maybe myself last year? Okay. So what do we call this form? Yeah, we call this thing factored form. And right now, folks, we're not gonna play with factoring just yet. We'll do that in Unit 4. And factoring, I'm going to tell you right now, factoring, you hear the word factoring, you probably talk to some friends in grade 11 and they say, hey, grade 10, you got to learn how to factor. And it's a very important thing. And I'm totally willing to spend all the time in the world on factoring because it's something very similar to kind of like quadratics. Like, it's a big part of quadratics, and it's one of those things that kind of just don't fade away over the course of high school math. Now, why do we like factored form? Like right now, you're probably just going to write this down, and you've got to take my word for it. But in the next slide, we're going to graph these quadratics in factored form and then kind of analyze what they look like. So it all kind of comes together. So the first thing that's lovely about factored form is that both factored form and standard form share that same A value. It's the exact same. So the A value still tells us the direction of opening, and that's why we keep that variable the same in factored and standard form, A, because they do the exact same thing in both of the forms. How about something else? The next best thing about factored form is that we're able to just look and point at the x-intercepts, or we call them the zeros, or the roots. Remember, there's like 100 names for these types of things. And the roots, or the zeros, or the x-intercepts, those are r and s. That's what they are. So when you're looking at something in factored form, you're basically looking at the x-intercepts, which are, in fact, symmetrical in quadratic on a parabola. And once you have x-intercepts, or even like a pair of symmetrical points, life is pretty good. Oh, also, we're able to calculate the vertex. So the vertex, which is the x values here, we're going to basically do x equals r plus s divided by 2. And that's kind of what we did in number 9 in the homework. We take the two symmetrical points. In this case, we have r and s. We're going to add them together and divide it by 2 to find the average of there. And that'll first give us this axis of symmetry. That's really what this is. From this axis of symmetry, we know that the vertex lies directly on it. So what we can just do is just take the axis of symmetry and sub it back into the original, and we can get the optimal value. Lastly here, axis of symmetry, is the x value of the vertex. Okay, this is great information, but again, at this point, This is good stuff. But at this point, it's not going to mean a whole lot to us, me just talking about it. It's going to make a lot more sense when we go ahead and start working with quadratics in this factor. Okay, more time? All right. Okay, here we are. We have two quadratics, both in what we call factored form. Notice we have y equals a, x minus s, x minus r. Is it s then r? Yeah, s then r, okay. And from this factored form, we're going to be able to just get all of this information without even graphing it, really. But it does kind of help to see a graph, especially when we're learning these types of things. So what I'm going to do is I'm going to hop over to Desmos, and I'm going to type in this quadratic, this first one here. I'm going to highlight it in yellow. So can someone maybe read this to me? We got y equals 2 bracket.
Close bracket.
Yeah.
Bracket again, x plus 2.
X, okay, lovely. So here we are. This is what it looks like. The question asks, first, what are the zeros, right? What are the zeros? And in the slide before, we said the zeros are quite literally the values of R and S. Now let's go ahead and look at what Desmos is saying to us. Oh, okay, here are our zeros. Now look carefully at these zeros, or x-intercept. We have -2 and +4. -2 and +4. If we have a look here, in the brackets we have x minus 4 and x plus 2. So it's almost like, do you see what's odd about that? It's almost like the signs are kind of reversed in both of them, but they kind of have to be, because the original here, it's x minus s and x minus r. So when you're subbing in a negative in there, it's going to look positive. And if you sub in a positive, it's going to look negative. So what we do, and I think a good reason why we're able to call these things zeros, is we're going to take the x minus 4. First, we're going to take this x minus 4 here. No bracket, sorry. We're going to take this first one and make it equal to 0. Yeah? That's kind of the reason why we call them zeros. And what we're going to do is just solve for x. So we're going to bring that -4 over, and x is going to equal positive 4. Not bad. Right? And how about this one over here? We got x plus 2. We're going to set it equal to 0. And we're going to bring this +2 over here, and we get x equals -2. So these are our zeros, +4 and -2. And if we go back to Desmos to confirm this, +4, -2. Not bad. So far, so good. Maybe we can write a little note to ourselves. Set the brackets equal to 0. You know, set something like that. Whatever's in the brackets equal to 0. Now they want the equation of the axis of symmetry. Well, let's have a look. Very similar to that homework question, number 9. We need the middle of 4 and -2. Now you probably could count with your fingers, but sometimes it might not be that simple because the numbers might be too large or something like that. So what we can do really quickly is just do the axis of symmetry is going to equal s plus r divided by 2. So this right here is s. This right here is r. So we're just going to sub those in. We're going to say, okay, this is going to be 4 plus -2 divided by 2. And we get something like 2 over 2, which equals 1. So our axis of symmetry exists at x equals 1. And if we go back to Desmos and we're going to type in an axis of symmetry, does that look like a good axis of symmetry? Absolutely. That looks kind of perfect. Okay, now, the vertex. The thing about this vertex is that the vertex exists directly on the axis of symmetry. And for that reason, we know the axis of symmetry is at x equals 1. And the vertex, of course, like we have it here on Desmos. But we shouldn't be too shocked that the vertex and the axis of symmetry share that same x value because the vertex lies directly on this vertical line. So yeah, when we have the axis of symmetry, we kind of have half the vertex. We have the x value of the vertex. So what we're going to do is we're going to take this x value of the vertex and we're going to substitute it into the equation to get the output, which would be y, or the dependent variable. So we're going to, maybe we can write a little note here, sub in axis of symmetry into equation. So our equation here is y equals 2 bracket x minus 4, x plus 2. Great. And we're going to sub in x equals 1. This is the axis of symmetry. So y equals 2 bracket 1 minus 4, and also 1 plus 2. You probably could just do this in one shot in your calculator, but we're going to bedmass this. 1 minus 4 is negative 3, right? Yes, okay. 1 plus 2 is positive 3, okay? Right? I think so. 2, just for the sake of space, I'm going to do it all in one shot here. 2 bracket negative 3, close, open, positive 3, close, equals negative 18. We're not shocked by that, right? Like we saw it on Desmos. So the vertex is 1 comma negative 18. Now the y-intercept. Now if this were in standard form, we would just say that it's the c value, right? But it's not in standard form, unfortunately. But let's have a look on Desmos to see where the y-intercept is. The y-intercept is down here at negative 16. Well, just like lines, if you want to solve for the y-intercept, you're going to have to set the x values equal to 0, right? Just like any function, really. So we can go ahead and say, okay, well, y equals, there's not a ton of room here, 2 bracket, we're going to sub in 0 minus 4 and 0 plus 2. So we'll get something like 2 bracket negative 4 close positive 2. I'm going to go right to my calculator. 2 times negative 4 close open positive 2 close. We get y equals negative 16. So the y-intercept is at 0 comma negative 16. There's actually more space for the direction of opening. Oh, that was silly. Okay, direction of opening. Whenever we're looking at that, we go right to that a value. The a value in both standard form and factor form are the same. And notice that this a value up here is positive 2. Yes? So this is open up or down. The a value, it's the first one here. So in the y equals a, x minus s, x minus r, it's this right here. There. So the a is positive 2. We can even write that down. A equals 2. Therefore, we can say this opens up. And also, we saw it on Desmos, this thing opens right up. that purple parabola. Now, because this thing opens up, it's smiling. Does that create a maximum or a minimum? Minimum, yes. And in brackets, we could say it opens up, silly. That's a minimum. And now, what is the maximum slash minimum, or what we say here is optimal? That's what we're used to seeing. What is the optimal value? Yes, negative 18. We're just looking at the y part of the vertex. Great. That is the lowest point. Right here. I'll try to zoom in, but this mouse is a little funny. Okay. So far, so good? Yeah, oh yeah. Now this next one looks a little strange, doesn't it? This negative 4 x minus 4 squared. When you see this squared here, what it really means is this. Negative 4, and then it's x minus 4, like that. That's really what it means. But math people always put things in simplest form, so anything multiplied by itself, like x minus 4 times x minus 4, is really just x minus 4 squared, right? So this is the way they kind of give it to us. Now, if we wanted the zeros, s and r, it feels like we only have how many zeros, do you think? Well, okay, sure, we have 2. They're both x minus 4. The other one's x minus 4. But when we go ahead and solve that, right, x minus 4, we'll set it equal to 0. X equals positive 4. R, it'd be like, okay, well, I guess it's the same thing. X minus 4 equals 0. X equals positive 4. It's the same thing twice. So how many zeros or x-intercepts do we have here? Just one. And that, remember the other day I told you, this is a special case when we have one x-intercept. Let's see what it looks like. Y equals negative 4 bracket x minus 4 close bracket to the power of 2. Look at what this looks like here. One x-intercept, or 1, 0. When there's 1, 0, that kind of informs us that it has to be the vertex. There's no other way a parabola can have 1, 0 if it's not the vertex. It has to be the vertex. Now, if you were given this type of question, the rest of this kind of just falls into place, but we're going to follow the same sort of sequence that we did here. The axis of symmetry. So the axis of symmetry is s plus r divided by 2. And really that's 4 plus 4 divided by 2, which is 8 divided by 2, which is just 4. And we're not too shocked by that, especially after seeing what this thing looks like. AOS stands for axis of symmetry. So now in order to determine our vertex, what we're going to have to do here is we have half of it already. We know the vertex is right now going to be 4 comma something, and we don't know that something just yet. But to get that, we're going to substitute the value of the axis of symmetry into the original equation. So the original equation, it's not that one, it's this one, negative 4 x minus 4 squared. And we're substituting in negative 4 for x. Sorry, positive 4. Positive 4. Well, what's going to happen here is we end up with negative 4 times 0 squared And 0 squared is just 0. And negative 4 times 0 is just 0, of course. So our vertex ends up being 4, right, from the axis of symmetry, comma, 0. And this, again, reiterates the fact that the vertex is the one and only x-intercept. And we kind of knew that because we graphed it on Desmos. Okay, the y-intercept, that occurs when we set the x value equal to 0. So we're going to go ahead and sub in 0 for x. Is that enough? Come in. Oh, no, it's not. It's enough.
I'm leaving today to the students, and I'll be back at the end of the period to go with my thing, okay?
Is there anything else we need to know?
Yeah. Joey's got a joke in the day.
Oh, yeah? What are you, sorry, say to the whole class, what are you going to do?
What is a computer's favorite snack?
What is a computer's favorite snack?
Computer chips.
Computer chips. Thank you so much.
Thank you.
Take care. Yeah. After this slide, we're gonna-
Okay, let's continue with this thing here. We got negative 4 times negative 4 squared, which is positive 16. And negative 4 times positive, is that what it is? Lovely. Negative 64. Good. This is our y-intercept at 0, comma, negative 64. Let's go ahead and double check that. That seems a little wild, doesn't it? Oh, okay. And Desmos is so good. Look, it kind of knows. Like it looks like it might be up there, but Desmos is like, no, 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 no. This is the one you're looking for. Beautiful. That makes me feel a little bit better. Okay, folks, direction of opening, up or down? Down, because we have a negative 4. And when this thing opens down, it creates a maximum. And the maximum value is the y portion of our vertex, which is 0. Right? The highest point of this thing is 0. Does that make sense to us? Does that look like it'll, yeah, okay, good. I know, it's brutal. It's brutal. Okay, folks, given this parabola, we're really good at this. We're really good at this. What are the zeros? Can someone tell me? What are the zeros here? This is kind of like a recap, right? Yeah, what do we got? Yeah, we got negative 1, 0, and 3, comma 0. These are the zeros, or what we might say, x-intercepts. Okay, axis of symmetry. Okay, we got, that must be x equals 1. And sure, what we could do is negative 1. Oh. You good? Am I good? Free. What was free? The apples? They were free. So from here, it's like our S value is negative 1, our R value is 3. So if you wanted to do axis of symmetry, right, the S plus R over 2, you're going to get the same thing here. Negative 1 plus 3 over 2. You get 2 over 2, which is just 1. Just to show you that it does really make sense here. Vertex, this is going to get the red 3 here at 1, comma 16. put a V beside it because it's a super important coordinate, because it tells us axis of symmetry and optimal value. Y-intercept, 0, 12. Direction of opening, down. That creates a maximum. And the max value is 16. Not too shabby. Now, sometimes when you're given the graph, it's really simple. And I know it's simple because you guys are so good at this. This is like the first 2 days of this whole unit. When you're given the equations, it could be a little bit complicated. But sometimes, and a great question to ask is right here. How might we get the equation of this quadratic? We don't have the equation of this quadratic, do we? Let's just say we wanted it in factored form. In factored form, what might this thing be in factored form? What do we got in this next one here? So what are our x-intercepts here? Because that's what factored form is all about, right? Like we got y equals a bracket x minus s. I don't know what happened there. And x minus r. And we know that s and r are the x-intercepts. We got s is -1, r is +3. The only thing we don't really have is the a value, right? Like we don't actually have that. We truly don't. So how about this question here? It says -2 and 4. Oh, I thought it was the same. Brutal. Let's just say we have a brand new parabola. We have the zeros, which are the x-intercepts. One's at -2 and one's at +4, okay? Then they also tell us this. They say, well, this parabola crosses the y-axis at 12. Determine an equation for the parabola and its vertex. Okay. First things first. These are x-intercepts, so this one could be s and this one could be r. Agreed? Great. It says they give us a coordinate, and when any sort of function crosses a y-axis, we call that the y-intercept. Yeah? Now the y-intercept is also a coordinate. It's 0, 12. So if we're going to start off with factored form, the equation in factored form is y equals a bracket x minus s, x minus r. We're going to substitute the values of s and r here. Y equals, we don't know a, but we do know x minus, what we're going to do here is sub in -2 and x minus +4. Agreed? Okay. Now, this is sometimes the strangest part. See this, what's going on right here? If we're going to simplify this, you already can kind of see what's happening. This is going to simplify to x plus 2 and x minus 4, right? It has to. When you subtract a negative, it's like adding a positive. So that's kind of the reason why if we're going to grab the zeros out of a factored form, they kind of change their sign. That's what's happening in there. Now, is that the equation? I mean, I wish it could be, but we just don't have the a value. How might we get the a value? Well, if we're going to solve for any variable in any sort of equation, it has to be the only variable there. Can we substitute something in for x and something in for y to solve for a? Well, thankfully, they gave us one coordinate, the y-intercept. 0 is x, 12 is y. So we're going to maybe write a little note here. Sub in 0, comma 12. So we can say here now 12 equals a bracket x is 0 plus 2 and also 0 minus 4. Right, we're subbing in 0 for x and 12 for y. And off we go. 12 equals a bracket 2 bracket negative 4, something like that. Now what's happening between the a and the 2 and the minus 4? What operation is going on between all three of those things? Multiplication. So we'll get something like 12 equals, well, a times, I guess, negative 8, I suppose. That looks a little funny to me, right? A times negative 8. So we're going to try to maybe rewrite that as negative 8a, because that's the same thing as a times negative 8, and that might seem a little bit more familiar to you. So at this point, if we're trying to solve for a, what do we got to do to solve for a? We don't want negative 8a, we want 1a. Yes, so it's multiplying, but so when we do that, it's kind of like dividing now. Yeah. I like to balance the equation. I like to divide this by negative 8, divide that by negative 8. 12 divided by negative 8. It's going to give us a fraction here. Negative 1.5, I feel like that's kind of reasonable to put as a decimal. It's a terminating decimal, which means it ends. So negative 1.5 equals a. I like that. So therefore, the equation here is y equals negative 1.5, open bracket, x plus 2, x minus 4. And I stole that from like this line right here. Now I know it said it wants the vertex, but I think just for the sake of time, and I'm just going to cancel that out, because I know once you're given this type of thing, we're just doing exactly what we've already done in this lesson. Okay, you know what, actually? I think I'm going to scrap this one. I'm going to scrap this question, and we are going to get the vertex of this instead. Because this is quite literally the same thing as the one above. I think I like that better. Okay. So in example 2, not even example 2, we're just going to say it's vertex time. We want the vertex of this guy here, negative 1.5, x plus 2, x minus 4. We want the vertex here. So to get vertex, think about it, we need x-intercepts. We know what the x-intercepts are. The x-intercepts are at negative 2, 0, and 4, 0. We knew that from the original question here, right? They tell us s is negative 2, r is positive 4. Yeah, maybe we can even write that. S we know is negative 2, r we know is positive 4. So to get the vertex, we need the axis of symmetry. And to get that, we're going to add the x-intercepts together and divide it by 2 to get the average. We have negative 2 plus 4 divided by 2. We get 2 over 2, which is 1. So the axis of symmetry is right here at positive 1. Now what we do with this is we're going to sub in into our equation. We're going to sub in the axis of symmetry into our equation. So we get y equals negative 1.5 bracket 1 plus 2 1 minus 4. And when we bedmass this, we'll get something like 3 and negative 3. So I'm going to go right to my calculator. Negative 1.5 times 3 times negative 3. And we get positive 13.5. 9 times 1. Yeah. So here we are. Therefore, the vertex is at 113.5. Now that's a pretty large type of question. Getting the equation and doing that. What we could do is also double check all of this on Desmos by taking this y equals negative 1.5 bracket x plus 2 x minus 4. Okay, so positive 4, negative 2 looks good. Vertex at 1, comma, positive 13.5 looks great. Okay, folks, I know we went right to the wire here. Don't forget though, tomorrow we're doing some mid-chapter review. So it's just basically like, okay, let's do some math here to kind of make sure this all kind of sunk in. And then, of course, we have this homework here. I'm going to give you a beautiful practice quiz. And we'll be on our way. Sound good? Okay.
Jack, if I understand it all, do I